Today we have Letizia Angeli, who's a PhD student at Warwick with Adam Johansen and Stefan Grosinski. And Letizia should have spoken last March, but then Corona happened and we were trying to put her in real life, but it takes forever. We don't know when real life talks are going to be back, so here it is. So please go ahead. I'll mute myself.
Okay, thank you for the invitation. And today I'd like to talk about interacting particle approximations of Feynman-Kac's formula for pure jump processes. This is a joint work with Adam Jansen and Stefan Grosinski. And the initial motivations arises from statistical mechanics, where there is a huge interest in studying the large deviation of stochastic processes. For instance, in the study of chemical reactions, glassy dynamics, or in the study of fluctuations of particle current in lattice gases. However, as you well know, when you want to study the rare events, you cannot really simulate the true dynamics over and over. So we are interested in studying some numerical procedure such that favors the realization of rare events. One such numerical procedure that is widely used in statistical mechanics is the cloning algorithm, which was introduced in 2006 by Giardina, Kurchan, and Peliti. And it's already widely used in statistical mechanics, for instance, in all these contexts. However, the cloning algorithm has aneuristic constructions, and there are only limited results about the convergence property of the algorithm. And in particular, they are mostly limited to the discrete time case. So the goal of our project, one of the goals of our project was to provide rigorous mathematical justification for the cloning algorithm in the context of pure jump processes in continuous time. And for doing this, the basic idea was to interpret the large deviations in terms of Feynman-Kac measures. So we can see the cloning algorithm as a particular interacting particle approximations of Feynman-Kac measures. This way, we can use already established results from standard sequential Monte Carlo methodologies based on mean field particle approximations, mainly from the work of Del Moral, Miklo, and Rousset, and applied these results to a broader class of interacting particle approximations that also includes the cloning algorithm. So this way, we obtain convergence results for the cloning algorithm. And today, I focus on the LP convergence of the algorithm. And the second thing we obtain is a framework with general and easy to check assumptions for an interacting particle approximation to check whether the LP convergence holds. So as I said, we work on the setting of Markov processes. And so quickly, we introduce a continuous time pure jump Markov process on a locally compact state space. And throughout the talk, I will use this notation. I denote by lambda the escape rate at a state x, by p the probability that there is a jump from a state x to a state y when a jump occurs. And finally, I denote by w the overall transition rate. So we can write the generator for a pure jump Markov process, the generator L, in this form, which is written in terms of the overall transition rate. And I will use this notation throughout the whole presentation. So once we have introduced a pure jump Markov process with generator L, and once we introduce also a potential function V, we can define the Feynman-Kac measures, where this is the unnormalized Feynman-Kac measure. And we also introduce the normalized Feynman-Kac measure mu t. What we want to do is to construct interacting particle approximations that approximate the normalized measure. And once we found an estimator for mu t, we can also construct estimators which are unbiased for the unnormalized measure using this relation. However, today I only focus on the estimators for the normalized measure. Before constructing the interacting particle approximations, I recall that mu t satisfies this evolution equation, where L is the generator of the initial pure jump process, V is a potential function, and this is an extra term which gives a nonlinearity of the process, and it depends on the current distribution itself. Keeping in mind this evolution equation, we can see that we can interpret mu t as the law of a stochastic process, which is associated to this generator, where, as I said, L is the generator of the initial pure jump process, and we call this part the mutation part of the process. And a second part, L tilde, which we call selection part. It depends on the distribution itself, and it is the generator of a pure jump process such that it satisfies this condition. The choice of L tilde is not unique, and if it satisfies this condition, we can see that replacing this into the evolution equation, so here we have L tilde f instead of this, we obtain indeed the evolution equation of a stochastic process. And we call this stochastic process the McKean interpretation of the Feynman-Kac measure. And as I said, the selection part L tilde is not unique, and we can, for instance, construct L tilde in, for instance, this form, where it also depends on the distribution itself, and W tilde can be constructed in terms of V in different ways. These are two standard examples. So once we choose our McKean interpretation of the Feynman-Kac measures, we can then introduce the interacting particle approximations. An interacting particle approximation is simply a family of n-particle systems, and we denote by mu and t the empirical distribution. What we want is for the empirical distribution to be an estimator of the Feynman-Kac measure mu t, and in particular we want to find conditions such that the LP error goes to 0 as the size of the system goes to infinity, and furthermore with order of convergence 1 over square root of n. Before introducing the conditions, I want to briefly illustrate two examples of interacting particle approximations. So the first one is a mean field particle system, and the second one is a cloning algorithm. The mean field particle system consists simply in running in parallel n copies of the McKean dynamic. So for every copy, we have mutation events and selection events. The selection events, since they depend on the distribution itself, and in this case it is the empirical distribution of the system, we can see every selection event as a cloning event. So we have that a particle of the system is cloned and another particle is killed. Keeping in mind this cloning interpretation of the selection events, we can then describe also the cloning process. The idea is to perform the cloning events for a particle only during the mutation events. And also it's possible to have multiple selection events at the same time. So for instance, for this particle, when it mutates, it's cloned twice, and at the same time, 2 particles from the system are killed, so that we keep the size of the system constant. Okay, keeping in mind these 2 examples, I introduce the assumption for having the LP convergence. So the first assumption does not depend on the choice of the interacting particle approximation, and it is just an assumption of asymptotic stability on the Feynman-Kac measure. Then the assumption on the interacting particle approximations are the following. First, we assume that the initial configuration of the system is independent, identically distributed accordingly to the initial distribution of the Feynman-Kac measure. Then we assume the following on the generator of the system. So to better understand this condition, I recall that the generator of an interacting particle system is connected with the expected behavior of the observables. So what we want here is for the trajectories of mean field observables, which are functions in this form, to coincide with the average of the trajectories of the McKean interpretation that we have chosen. Then the next condition is on the Carré-Duchamp. So the Carré-Duchamp is a quadratic operator written in terms of the generator of the system, and which is connected to the fluctuation of the system. So the idea here is for the trajectory of the system to concentrate on their expectation as n goes to infinity. And finally, we assume that the number of particles that change value at any given time t is bounded by a constant independent of n. So for instance, if we consider the mean field particle system, we have that at every mutation, only one particle mutates, and at every selection, only one particle is replaced. So for instance, in that case, k is equal 1, and we have this condition satisfied. To better understand these 2 conditions on the generator and on the Carré-Duchamp, I show you that they're both satisfied for mean field particle systems. And I also show you how to construct a cloning algorithm so that we have these 2 conditions. Okay, so first we start with mean field particle approximations. As I said, it simply consists in running in parallel n copies of the McKean process. So of course, the assumption on the generator is satisfied. Secondly, we can also write the Carré-Duchamp of the mean field particle approximation in terms of the Carré-Duchamp of the McKean model. So from this relationship, it's easy to see that the condition on the Carré-Duchamp is satisfied. Then it's a bit more involved, the discussion for the cloning algorithm. And for checking that the condition on the generator and Carré-Duchamp are satisfied, the first step is to explicitly write the generator of the system. I try to briefly describe why we have this generator for the cloning algorithm. So the idea is that for every particle I of the system, the particle I mutates with rate lambda, which is given by the mutation dynamics we had at the beginning. Then with rate lambda, the particle I mutates to a new state Y with probability P, which is also given by the mutation dynamics we had at the beginning. Then at the same time, we have a cloning event for the particle I, and it can be described as follows. So we select a set A from the populations, and we replace every element of A with the particle I, with some probability P. So this notation simply means that we have the configuration, we have the same configuration, but the elements of A are replaced by the particle I, and that the particle I is replaced, mutates to a new state Y. So what we want is to construct these probabilities pi such that the assumption on the generator and on the carré Duchamp holds. First, we start with the assumption on the generator. And the only condition that we need for pi is, so essentially what we want is the probability of having an element J replaced must be written in terms of W tilde, which is given by the selection part of the McKean model we chose before. So writing the probability of selecting and replacing a particle J in terms of W tilde, in this way, we obtain that this condition on the generator is satisfied. And secondly, if furthermore we assume that the probability of replacing an element J and an element K different from each other, so the probability of replacing J and K is bounded by this quantity, then we also obtain that the condition on the carré Duchamp is satisfied. And this holds, for instance, if we just assume that every element J is replaced independently from all the other elements from the population. So more in general, if we have an interacting particle approximation, and if we want to check that these conditions are satisfied, we have simply to write down the generator and with some computation see if these are satisfied. So it's pretty easy to check. And also, it can be useful to interpret these three assumptions on the interacting particle approximation through Martingales. Indeed, by the condition on the generator, we obtain that this process is a Martingale. Then, using the condition on the carré Duchamp, we have that the predictable quadratic variation of the Martingale, which is associated with the carré Duchamp, is bounded by this quantity. And finally, we obtain that the jumps of the Martingale, which are connected with the jumps of the interacting particle approximations, are bounded by this quantity. And using this interpretation of our conditions, we can then use also this key tool on Martingales, where we can write this, where n is a square integrable Martingale, in terms of its predictable quadratic variation and in terms of the bound of its jumps. So this is the key tool we use in the proof for the bias and LP error estimates. And this is the final result we obtain. And so as you can see, we have a bias estimate where it is it converges to 0 with order 1/n, and LP error estimate that converges to 0 with rate 1/√n. And this is consistent with the results from the standard sequential Monte Carlo methodologies. And this result is based on a joint paper with Adam Johansen and Stefan Groskinski. Okay, thank you for your attention.